So we've been talking about ideal gases for a while now, and those ideal gases are described by the postulates of the kinetic molecular theory. And so two of those postulates are assumptions that we can't make in all conditions. And so those two postulates that we have listed here are, the particles are so small compared to the volume of the container that they are in that the volume of the particles can be ignored. And the second postulate, the gaseous particles are not attracted to or repelled by one another. So think about it like this. There are two conditions that these postulates can't really be made in. And so gases deviate away from ideal behavior at low temperatures and high pressures. And so why is that? Well, if we consider this first thing here, where are you? Oh, it's over here. No. So consider the second or the first postulate, which is the gas particles are so small that we can kind of neglect their actual volume. Well, that makes a lot of sense when we're talking about vast volumes where the gases occupy a pretty small space compared to the relative amount of empty space. And so what happens then if we compress it and we put a lot of pressure on it? Well, it's going to be a lot harder to actually ignore the actual volume of the gas when it makes up a lot more of the overall space of the container that it's in. And so that's why high pressure is such an issue here. And the other one stems a lot from like interactions of gas molecules, because we assume that gas molecules are just these perfect little particles that if they collide, they just bounce straight off of each other. They perform elastic collisions. But we know that, especially with with molecules that have a lot of intermolecular attractions, and just to recall here, intermolecular attractions are things like ionic bonds, hydrogen bonding, dipole-dipole interactions, or van der Waal interactions. All of those different interactions are going to affect the way that molecules interact with each other. Because if I have one H2O molecule and it comes near another H2O molecule and it hits the other one, it's not just going to bounce perfectly off. At least in our ideal conditions it will, but in the real world there's a good chance that those hydrogen molecules or those water molecules are going to come near, and even when they're about to interact and after they interact, they're going to have this slight intermolecular hydrogen bonding. So they're going to have a slight attraction to one another because it's more stable just to hydrogen bond than it is just to float in the empty atmosphere. So as we move particles slower, right, at low temperatures, these molecules have more time to interact with each other, which means they have a higher possibility of losing some of their momentum as they come close. And that loss in momentum could cause a deviation in its behavior from the ideal gas law. So all of this is just a summary of ideal gas laws concern ideal gases, which are pretty theoretical. Damn, as much as I like what I just said, it's not perfect. So now that we've talked about ideal gases, the postulates of the kinetic molecular theory that talk about the properties of ideal gases, now we need to talk a little bit about non-ideal gases. And so there's two postulates of the kinetic molecular theory that can be broken in certain situations. And those two postulates are that particles are so small compared to the volume that the actual volume that the particles occupy can be ignored, and that particles are just these perfect substances that don't interact with one another. As soon as they collide or they come near, it's just elastic. They'll just go right past without any real attraction. Or if they do hit each other, they just bounce back perfectly with no real attraction or repulsion from one another. Now, that's not going to be true. And it's really not going to be true when we talk about gases that are at low temperatures and high pressures. And there's a reason for that. So when we talk about high pressures, think about it like this. When we have gases, we usually think of this gas in a very large, expansive, empty space. And so when the overall gas molecules, if I compress them all, took up such a small fraction of the overall volume, I can just say, hey, it's negligible. Even if I consider the volume of those gas particles, it's not a real major contributor to the overall space. But in high pressures, after I can compress this gas, because gases are compressible, the more I compress this gas, the less volume the overall container has, and the more that these gas particles will contribute to the overall volume. So at high pressures, gas particles are one, a lot closer. So because they're a lot closer, they have more possibilities to interact. And two, their volume now contributes a lot more to the overall volume of the container. So that is the effect of high pressure. Now at low temperature, these gas molecules move slower because kinetic energy, the speed, is directly proportional to the temperature. So when I compress a gas, the molecules are going to be moving a lot slower. So if they combine one another, they have a lot more opportunities to have some kind of attraction or repulsion. And it doesn't matter which attraction we're talking about. And we have to kind of like just say real fast, when I say attraction, I'm talking about intermolecular attractions. So if I have two H2O molecules, H2O molecules like to hydrogen bond to each other. So hydrogens of one H2O molecule, the oxygen of the other H2O molecule, they like to really kind of interact with each other. And so if I speed them right past each other, they don't have much time to actually interact. But if I take them very slowly, right next to each other, and especially when there's not much volume to the container, so there's a lot of crowded H2O molecules, they have a lot more likelihood of interacting with each other and kind of starting to hydrogen bond. And so when they hydrogen bond, they start to kind of have a non-negligible attraction. And so it doesn't matter which intermolecular attraction I'm talking about, whether it's ionic, whether it's hydrogen bonding, whether it's dipole, or whether it's van der Waals forces. All of those forces, all those intermolecular attractions play a role. And so that second postulate, the gaseous particles are not attracted to or repelled by, is pretty hard to make. And both of those postulates play a big role in the ideal gas law because the pressure and the volume are major units or major variables in ideal gases. So what can you do if your ideal gas no longer has a pressure that can be ignored because now you're breaking postulates, or a volume that can't be ignored because now you have higher likelihood of attraction and more space occupied by the gas? You can start to add corrective units, which means we're going to take the ideal gas law and we're going to now add in some new variables that will kind of make up for the deviations from the kinetic molecular theory. So, do you need to know this formula? Not really. Do you need to know how to do calculations? No. What you need to know is what A is and what B is. And so what we're talking about, remember, are the attractions are a big issue and the volume is a big issue. So A is going to correct for the overall attraction that molecules feel. So when you have an attraction, you can't make one of the postulates, and now you need to account for that. So you do that by giving the value of the, or you do that by describing A, or putting A in as a variable, which is now, we're going to take this attraction into consideration. So A is attraction. B is the size of the particles, because when we now compress this gas, the size of the particles matters a lot. And so it's kind of easy to remember. A is attraction, B is the other one. And as long as you know its attraction and size, you can start to kind of figure out a lot of different variables. But the most important thing is, if you're going to get asked a question about this, it's just going to be one or two things. Which one of these different gases has the largest value for A, or which one of these variables has the largest, or which one of these gas particles or gases has the largest B value. And so just so we know, we already said that this is about intermolecular attractions. And so what are the intermolecular attractions? Ionic attractions, hydrogen bonding, dipoles, and van der Waals/London dispersion. So ionic, hydrogen bonding, dipole, and let me just get rid, dipole, and then London dispersion. Ionics will have the highest A value. Come on. And then London dispersion will have the lowest A value. Cool, and I'll just highlight that, because that is the main takeaway here. The rest is theory, but baby, if you don't know the A values and the B values, you're in trouble. So what will be, what will the, what will be the trend for B? Well, largest radius will have the largest B value. And it's really that simple. But if you have no idea what A and B are, you're in trouble. All right, now let's look at some practice problems. So example 8M, using the van der Waals equation, which of the following gaseous molecules would you expect to have the highest value for A? Well, so for A, we're talking about the attraction. And so if we're talking about the attraction, we're looking at the strongest intermolecular bonds. So we have three molecules here. We have NH3, CH4, and CCl4. So what are the attractions that each one of these molecules have? Well, NH3 has hydrogen bonding. Remember, hydrogen bonding is just going to be NOF. Nitrogen can do it, oxygen can do it, fluorine can do it. So it has hydrogen bonding, it would have dipole as well, and it would have London dispersion. Dipole because NH3 has a lone pair. It's not perfectly symmetrical, so it's polar. And then London dispersion, everything has London dispersion. CH4 does not hydrogen bond, it's not ionic. It does not have a dipole, so it only has London dispersion. Then what about CCl4? Same exact issue, London dispersion. It's perfectly symmetrical. So this question really comes down to, one, do you know what A is? You know its attraction. Do you, two, do you know what the strongest intermolecular attractions are? And then 3, do you know what hydrogen bonding is? So there's a lot of variables here. I guess the 4th is that, do you know polarity? And so do you know that the lone pair on nitrogen makes NH3 not symmetrical, while CH4, CCl4 are trigonal planar, and they actually are perfectly symmetrical, and such they are not going to have any kind of dipoles. They're only London dispersion. A lot of fun blabbering, but yeah, the answer is A. Now, definitely memorize the intermolecular attractions. If you can't name what intermolecular attractions any molecule has, you should practice it, because a lot of the times you're going to be asked, hey, this has what of the intermolecular attractions? And it's not just going to be, oh, it's hydrogen bonding or London dispersion. It's going to be, here are the 4. Which ones does it have and which ones does it not have? Just a bit of advice. Example 8n. Using the van der Waals equation, which of the following gaseous molecules would you expect to have the largest value for B? So B is the size. So which one of these gaseous molecules has the largest atomic radius, the largest size? Well, you can think about it 2 ways, really. Or mostly, honestly, just one way, which is Br2 weighs the most. It has the largest principal quantum number, n, which means it's going to have the most shells, which means it's going to have the largest radius. O2 is smaller, and H2 is the smallest. So A is the answer. Only thing I would be careful about here is, let's say if I was given, N2 versus O2, well, N2 is going to have the same principal quantum number as oxygen. And so if I had to pick between nitrogen and oxygen, even though oxygen weighs more, it's going to have a smaller atomic radius. Remember the atomic radii trend. So my answer would be N2 in that case, but coming back to example 8n, it is A.